So last week we talked about the anionic chain construction as a systematic way of realizing lattice models that have like a given generalized symmetry encoded into some spherical fusion category. Or as a way as well to, if you have a given Hamiltonian and if you rewrite it in the anionic chain language, then you know exactly what symmetry it's going to have by construction. So it can be also a way of identifying some symmetries in a model. So this anionic chain construction, let me just briefly review some references. So this first reference, this was where the construction first appeared. For a very specific example, it was the case of the Fibonacci category, so a category that encodes the Fibonacci anions. Some of the authors then generalized it for quantum deformation of SU2, so a broader class of fusion categories, but still not as general as what we talked about. I think the first time it was written down for an arbitrary fusion category were in this paper by Wickham and Gromov. The definition was, so the way I defined it last week and the way I started using it last week and we're going to keep using it today was a bit more specific to this, so our two references there. So like the notations and all, and the actual definition of the anionic chains I've been using, it's more specific to these two references. As far as the mathematics is concerned, so in this book you can find all the definitions and theorems we're going to use today in particular. So I encourage you to check this book if you want like more complete definitions and proofs of some of the theorems I'm going to use. Okay, so today what we're going to talk about is a generalization of the anionic chain construction. So a generalization that we established in these two references, which will all allow us to study dualities between quantum lattice models. And so first I need to introduce a mathematical definition, which I will motivate a posteriori, is the notion of module category. So essentially a module category is it's a bit like a module over a ring. It's kind of a categorification of this notion. So the same way you think of representations of a group, right? You can think of it as a module. It's something that is acted upon by the group. Well, here this is going to be the analog, but for fusion categories. We're going to look for stuff that are acted upon by the objects in some fusion category. Okay, so given a fusion category C.
Until now you only talked about spherical categories.
Yeah, so it's not required for this definition. Actually, you only need to be monoidal for what I'm going to talk about. So the input for the construction, we will still take it to be spherical, but as far as defining module categories is concerned, you don't need this additional structure. So a module, so a right module, we have left and right module categories. So I'm going to define a right module category of a C or a C module category. It's a triple. So we need three items to define a module category. First of all, we have a category that is nice. So nice in the same sense as fusion categories are nice. So I'm just going to put the adjectives here, but we won't worry too much about this. So we need this category to be finite, semi-simple, and linear. It's just so that everything is nicely behaves nicely, but okay, it's basically a category M. Then we have an action. So we have our fusion categories is going to act on this category. So we have an action. Like this. Okay. And then we have something that is the analog.
Which letter is this?
This?
Yeah.
No, it's a triangle to the left. And then we have something that is analogous to this associator of F symbols that we defined in the case of a fusion category. So we have a collection of isomorphisms often referred to as module associators. Which translate the fact that, well, let me write it down first. So it's saying that acting with two objects, or first fusing these two objects and acting with the result of the fusion, is not strictly speaking the same thing. It differs by some isomorphism. So in the case of the fusion category, remember there is an F, right? And the F is saying that the order in which you fuse objects matter. But here, this is the analog of this. It's kind of the order as well. It's just like we have two types of operations. We have the action, and we have the fusion of the objects. And these isomorphisms, they fulfill some coherence relation, which I will write down graphically after, the same way we did for the fusion category. So it's called a pentagon axiom, this coherence relation, and it will involve the F that is in the definition of the fusion category C. Okay? Before I do an example, we're going to, so at the end of the day, remember in the definition of the ionic chains, we don't really use these isomorphisms in this way. We want to write them down in terms of matrices, and then these are the matrices that we use. So we're going to do first the analog for these guys. So the way it looks like, I'm just going to give you I'm going to do it graphically the same way we did it last time. It looks like this. I'm going to try to use colors as much as possible, since now we have different types of objects. Okay. So here, these are the two objects x1 and x2. Then they act on an object m1. In the result of this action, and they can be simple objects m2. So then we have an isomorphism which we block decompose, like we did exactly for the F in the fusion category. And it translates into this graphical operation. Okay, and then on the right-hand side, okay, and the basis vectors and lm. Okay, and so this is, if you remember the drawing we had last time for the module for the F in C. It's something very similar looking. It's just that here that the leftmost objects now they have to be in the module category. The fact that we draw it like this as a straight line, it's not completely random. It's because this data, module category, it encodes as well the data of a topological boundary condition for the topological field theory that shares the same input C. So I briefly mentioned last time that this spherical fusion category, they can be used to build 3D TQFTs on the lattice. And in that case, these module categories are going to label the boundary conditions of these TQFTs. So this is partly why we also represent it like this. You should think of it as a boundary, so that there is kind of, it only acts from one side. So these guys are numbers, right? These are the matrix entries. So these isomorphisms decompose into blocks. Then you can identify matrices, and these are really the entries of these matrices. But at the end of the day, it's enough to remember this graphical rule, essentially. The fact that there is a basis here. This is a different basis. This matrix does the basis transformation, and these numbers, we call them so some, well, kind of F symbols in the same spirit of the Fs of the monoidal of the fusion category. So let me give you some examples right away so that we...
So can I just add, so the principal distinction between what we're doing here compared to what we did before is that now we have these m's and x's that are on different footings.
Mm-hmm.
That's the main generalization that we're allowed to.
Yes, in a second I will show you how we use that in practice. Well, in maybe 2 seconds because I'm going to do an example first. But yes, these module categories will enter now the definition of these generalized and unique chains.
In the old thing, X was doing 2 things, two roles, and now you can.
Exactly. So actually, this is kind of the first example. Is the fact that, which is kind of obvious, is that any so C is always a module category over itself. So secretly, in the last week, we kind of used that. I mean, from the perspective of these generalizations I'm going to talk about in a second, we were using C as some of like if you want the labels in the definition of the Hamiltonians, really we were using there the fusion properties, but then when we would act on the Hamiltonian on the Hilbert space, this is where we were using C rather as a module category. I'm going to clarify this when we do the construction. So this is the choice you can always have. It's the same as a regular representation of a group. You can always have. This is, sometimes we call this a regular module category, right? So this is an example you can, sometimes this is the only choice actually, but you can always do that. So another example that is more interesting are, so I'm called the indecomposable module categories. So indecomposable in the same spirit are indecomposable for representations of a group. Over, so one category that we talked about already, which is RepG. So this we know all of them. It's actually a result of Ostrich. We classified these indecomposable module categories. And they are all of the same form. It's a category of projective representation of some subgroup. So here, A is a subgroup, okay, and psi is a 2 cocycle of this subgroup. So it allows you to build projective representations. So projective representations, just saying that this is something that does not quite preserve the. Well, okay, let me just write it down. So projective representation pi satisfies this relation where you have the 2 cocycle that shows up. So in a linear representation, there wouldn't be any psi. A projective representation, it preserves the multiplication, but up to a phase, which is given by this cocycle over here, right? It's a cocycle. The cocycle condition ensures the fact that it remains associative. Okay, so how does it work? So this is, I'm just telling you that this is basically the objects in M are going to be of this form. They are going to be projective representations of some subgroup. Now, how does the action look like? So the action is via so what we call a restriction functor. It's something that is very natural actually. It's just saying that you restrict your representations. Every time you have representations of a group, you can always restrict them to representations of the subgroup, right? You just because a representation of group is in particular a representation of its subgroup. It may not be an irreducible, even if you start from an irreducible representation of the group, it may not be an irreducible representation of a subgroup, then you would decompose into irreps. So very concretely, what it means the action. So if I have a V, we do right action. So a V is a representation of G, and it acts on the representation of A. It just acts by, so you first take the restriction, and then and then you just do the tensor product. So it's at the end of the day, it's just the usual tensor product that we use. So of representation of A, right? And the F symbols in that case, well, they are defined exactly in the same way as the F symbols for rep G. We just take the Klebsch-Gauss coefficients and we contract them together, so you get some Raka, what we call the Raka or F symbols, or SIG-J symbols. So it's not, there is no additional data. I mean, in defining these F symbols, it just follows from the representation theory of the group.
Clément?
Yep.
Where is the information about psi in this restriction on the tensor product?
Yeah, well, it doesn't. Yes, so you can put psi there. It doesn't matter. I mean, it's gonna be. Then what you do is that you do the restriction. Well, so rather, no. Here I shouldn't. Sorry, I shouldn't put. What you do here is that this can be a projective representation. V you restrict it to representation of A. And then you can tensor a projective representation of A with a linear representation of A. It's just going to give you a projective representation.
From rep psi G, I can start from just rep G and then...
Yeah, so you start from rep G, there is no, the psi is not included there. You restrict to rep A, and then you act by tensor product. But what may happen is that indeed if M is a projective representation of A, then you end up tensoring a representation with a linear, and that's projective, right? Okay, so another example, which is a bit more difficult to do as explicitly, but I can give you at least the data, is the other main example we talked about, which is so this vec G alpha. Right, where the objects, you can think of them as essentially the group elements, and then there is this alpha, this cycle that then encodes some, well, I told you that it encoded some anomaly. So the indecomposable, so it's also a result by Ostrich. The indecomposable vec G alpha module categories. Well, it's very similar. Are labeled by subgroup, and the fact that it's very similar is not a coincidence, and we will see that maybe today or on Friday, by so a subgroup as well, and so this time a two chain, which is just a function of two group variables, satisfying a condition, which is that when you restrict, so the condition is that you can only pick subgroups such that the alpha, when you restrict it to this subgroup, I take the inverse, it's just a matter of convention. When you restrict it to the subgroup, so instead of evaluating it on any elements of the group element, you just evaluate it on element of the subgroup, it has to be trivial, which means it has to be of a specific form, and it means there must be a psi, well, it has to be a co-boundary. I mean, this is the cohomology terminology. And this psi, just essentially, you can think of it as trivializing this alpha. What is important here to emphasize is the fact that if I start from an alpha that is non-trivial, what it means is that I cannot express it in this form on the whole group. That's what it means. Which means that then I cannot choose G there as a subgroup. So actually I cannot, if alpha is non-trivial, I cannot choose the whole subgroup, because I can only choose a subgroup in such a way that my alpha is trivial on it. So here we already see this anomaly flavor actually, because this A here is going to control essentially what we gauge. Like as soon as we start talking about dualities, this choice of A will control of what amount of the symmetry we gauge. So we start from a G symmetry and we want to gauge A. And where we cannot, if alpha is non-trivial, we cannot actually choose G in order to build a module category. And this is where the obstruction is going to come from.
But it seems to be that the only thing which is going to break, that it's going to be decomposable.
So you can, it is possible that this is trivial on a subgroup.
No, what I'm saying is that because of your first example,
yeah. So there's first
G is always a modular category over itself, right? So the only thing which can break is that it's not going to.
So when you choose vec G over itself,
Yeah.
it means not doing anything. So it means not gauging anything.
Well, I'm not talking about gauging here.
Okay.
How does it fit into this classification?
So the fact that this is indecomposable, you mean? Is it the question? Why is it indecomposable?
Not indecomposable. That's the only thing which can break.
So it is indecomposable here means the fact that the object. So it's a bit more delicate to write down everything. In the case when there is no alpha, it's easier. But when there is an alpha, it's a bit harder to write down explicitly these symbols. But the objects, I can give you that the set of simple objects of this category. Which I'm going to write MA psi, is given by the set of cosets, which is a transitive G set for every A. So it doesn't split into orbits, right? Like any element, whatever A you choose, you will always be able to go through all of them by acting with group elements.
In fact, my only question was, so how does first example fits into the last example? So
for the very first example is just saying that you can choose vec G alpha to be a module over itself. Then it just acts by
choice of A doesn't correspond
to the trivial subgroup. Yeah, sorry. Well, yeah, in that spirit, right? So trivial subgroup. So then the quotient is trivial. It's just G itself, right? So the other extreme would be to be the whole group, and this would amount to gauging everything. Yeah. Okay, so now let's see how we actually use that in practice, right? So I'm going to call this the generalized ionic chain construction. And so just maybe to emphasize one more time, is that if alpha is trivial, then the data labeling these indecomposable module categories is then just a subgroup, and in that case this would be a cocycle because you don't have the alpha over there, so this would have to be 1. Then it's the defining property of being a cocycle, and so this is exactly the same classifications of this guy. Then they are classified by exactly the same thing, and that's actually a very important thing to notice. Okay, so the generalized ionic chains. So the idea is quite simple. The first thing we're going to do is that we're going to keep the exact same, what I call the abstract local operators last time. So I call the abstract local operators these operators that I defined graphically, right, with diagrams of this form, like I would take superpositions of diagrams of this form, but abstract in the sense that until I specify the way they act on the Hilbert space, you cannot quite write them as matrices, right, explicitly, right? So before you specify the action, you don't really know exactly how they act. But so these are exactly the same thing. The only thing we're going to change is that we're going to change the Hilbert space. We're going to change the Hilbert space, or rather we're going to define a family of Hilbert spaces, and this will depend on the choice of indecomposable module category over the input. So I have these Hilbert spaces that depend now on the choice of M, choice of module category, and they look well. Actually, since because of the notation I used last time, it's actually pretty much the exact same definition. So maybe let me try to use some color here. Okay. So I'm just changing. So the at the top, it's exactly the same as before. We had this choice of object X. This doesn't change. It's an object in C, right? So it's an object in C, right? But I'm changing the bottom a little bit. The horizontal labels, now I'm saying that they have to be valued in the module category. Okay. So we have our states are defined using these graphs like this, and so this span is over. It's over simple objects in M, and the basis vectors in the corresponding Helm spaces. The vector spaces that we have in Helm spaces, which are then in M. So let me rewrite it more formally. This is the same as this equation. But the main difference is that now these Helm spaces are Helm spaces in the module category. Okay. So here, when defining this Hilbert space in particular, and then subsequently the action of the operators on this Hilbert space, at no point we fuse these horizontal lines. We will never have to fuse these horizontal lines, which is what allows us to actually use module categories instead. So module category, you cannot fuse objects, you can act on them, but you cannot fuse them. And so we can actually do that because it never entered the definition of the Hamiltonian. So then the action of the Hamiltonian is defined in exactly the same way as before. I can redo it quickly. So it's like graphically, the only difference is that now we're going to use this sort of modified F move that is at the top there. So let me do that. I can do it at the bottom here. So the action. So we have. So remember, we would kind of stack the local operators on top of the state, right? And then we would just use repeatedly the move over there. So then I use it once to get something that looks like this. Okay. So here you see that I'm indeed using this one, that the blue lines, they don't move. I'm just recoupling instead of fusing first these two white lines, I'm going to act successively with them. And then we do it one more time. So we don't use the initial F anymore. We only use this new one. Like the blue, yeah, you don't see the blue really well. Yeah. Well, maybe just let me finish this one and then I will switch to another one. Yeah, sorry. Okay, and here we have something that looks like this. Okay, and then we can just pop this this bubble. Okay, so this is exactly the same as strategy. The only thing we change is essentially the Hilbert space on which we act. So now
with this new definition,
yeah.
Does the category C have to be spherical, or can it be a more general category?
So first of all, when
Construction to work for this section to work.
so okay, the sphericality condition, as I said, it was a bit. Some of the assumptions were like comfortable, so that then we wouldn't have to worry about some aspects. What we still need for sure, which was part of it, is a notion of dual object, for instance. We still want to be able to dualize these white lines, so this is fine. And we still want to be able to make sense of diagrams like this, which use some of the, so it's more like the so-called pivotal structure. The spherical is something slightly on top of that. I used sphericality because it was just easier then everything was included in there, but strictly speaking, we don't necessarily use it when we do this specific manipulation. Okay, so now the claim is that if you you choose a collection of local operators and you simply change this Hilbert space, these models are going to be dual to one another. so I will try to convince you that this is true, of course. But the part of the intuition comes from the fact that if you look at these examples over there, changing the module category will precisely correspond to gauging some of the symmetry, possibly in a twisted way. So if you include this psi, then it's not exactly a plain gauging. It's like you do something else at the same time. But this will simply amount to performing this task. Or rather, I should say, it's gonna do the analog of what we did for Kramers-Vanier in the first lecture, where it does the gauging, and then it kind of solves some of the constraints that appeared in the gauging, and then you trace away degrees of freedom. You disentangle as much the degrees of freedom as you can, and you sort of get rid of some of the initial matter degrees of freedom that you don't need. So it's more like this collection of steps. And so let me just illustrate this. So I'm gonna do a series of examples, but let me just illustrate what I just said at the level of the Hilbert spaces for one case. So if the input is vec_g, right? And I choose the object to be like we did for Ising. The example, when we did the example last week, we chose the object to be just the sum of all possible simple objects. In that case, the states, they had so we had states like this. So here, so let me choose the module to be also vec_g for now. And so what happened is that, okay, we had group elements over here, like this. And then we said that if you specify the group elements at the bottom, in order to have a non-trivial Helm space here, you have only one possibility for the object over here, which with our conventions means that it has to be equal to gi -1 - 1 gi, and so on and so forth. And therefore, we said that this Hilbert space was actually isomorphic to just something of this form. Because, so again, if you specify these degrees of freedom, these are constrained to be something. So you only have as many degrees of freedom as the number of sites. It's a tensor product space, and it's just this vector space. Now, what I'm saying is that, so let's say we can define some Ising model with that, or whatever model you think of. I'm saying that if you just replace this guy by something else, so let's do the extreme case which would amount to gauging everything. So this mg here, it's, as we said, it's the one where you take the trivial subgroup, right? Now if I change, if I do the opposite, where I take the whole group instead, I told you that the simple objects were given by the quotient, so then it means like the objects in the module category are given by the quotient of g by g, so you're left with basically nothing, which means that there are no degrees of freedom anymore on these horizontal lines. The only thing that survive are the stuff on the vertical lines. And so this is exactly what Kramers-Vanier does. Kramers-Vanier, it takes initial spin configurations. These are the domain words essentially between spin configurations, and by sort of switching off the degrees of freedom here, then you're only left with these things, and it's the statement that the domain words become the degrees of freedom. So I will redo it once we talk about how to write down the duality operators. I will redo this slightly more carefully, but you see, this is really the idea. So when I say gauging, I meant in the same way where here I wouldn't be left with any matter degrees of freedom anymore, right? I gauge and I disentangle, all the matter degrees of freedom become classical, and then I'm only left with the gauge field, which are these domain words, degrees of freedom. Okay, so let's do some real examples now to really understand how this works. Okay. Yeah, of course.
And what will happen if you change x?
I mean, then so x is really so first of all, if you don't take this x, then you won't have a tensor product space. So you're gonna have a model that has some kinematical constraints. I explained briefly last time that if I take x to be sum of simple objects in a subgroup, then this would naturally give you something where you sort of break the symmetry. Like this, like if you want to write down a fixed point for a given gapped phase, you will typically choose X to be the sum of simple objects in a subgroup. So it will put some constraints. It doesn't change anything about that story. Here, X is completely arbitrary. It doesn't change. It's just that then you have a different type of model. Like, yeah. But okay, let's see. I'm going to do some actual examples now, and you will see the role of X and everything. Okay. So we're going to do 3 examples where we fix the input, the fusion category, and we're going to go through 3 different module categories to see what kind of dualities we can get of dual models. So the input we're going to choose is the category of representation of the dihedral group D6, so the smallest non-abelian group. So let me just briefly review some facts about this group. So first of all, I'm going to choose this presentation. So it's the group of symmetries of the triangle. So you have the rotations of the triangle, and you have the reflections. So the rotations are R, the reflections are S, and they satisfy, so it's non-abelian, satisfy this condition. The simple objects in there are given by the irreducible representations. So we have 3 irreps for D6. I'm going to label them 0, 1, and 2. So this is the trivial. This one will be the sine. And this one is the 2-dimensional one. And so they satisfy in particular these fusion rules. Okay. And this one. Okay, so that's pretty much everything we need to know. You can, and maybe just to be explicit, so for instance, the 2-dimensional representation of R, so I'm working with complex representation, it looks like this, and for S, it's just a Pauli X matrix with omega is exponential to pi I over 3. Okay. So from this, you can then compute in particular the Clebsch-Gordon coefficients of rep D6, and from that we can compute the F symbols in particular, because it's just the Clebsch-Gordon coefficients that we contract together. Now the Hamiltonian, so I'm going to fix a Hamiltonian or abstract Hamiltonian. I'm working with the periodic boundary conditions for now. We will discuss the twisted ones later. So it's going to be, I have two types of operators, which I'm labeling by some objects in the representation of D6. So here they will have the 2-dimensional representation, and here the sign one. And they take a very simple form, these operators. So I can define both at the same time. So y is either 1 or 2, the representation. And it's just one simple, one diagram. The x is fixed to be the 2-dimensional representation. So in that case, the x is a simple object. There is no multiplicity, so there is no freedom there. So it's quite simple in this way. Okay. So it's everywhere the 2-dimensional representation, and y can be either the sign representation of the 2-dimensional one. That's all. So it's a fairly simple Hamiltonian to define. But now we're going to see how it actually looks like once we choose a Hilbert space. Maybe I'm going to keep the diagram at the top. Where's the brush? So we know already what the indecomposable module categories over rep D6 are. They are given by the subgroups and potentially some 2 cocycles. Actually, in that case, none of the subgroups have 2 cocycles. So the only things we can choose are subgroups. So we have 4 subgroups. there is, well, the group itself, the trivial one, the identity, and then we have Z2 and Z3. And one way to see that immediately is the fact that this group is isomorphic to the semi-direct product of Z2 and Z3. So we're going to do 3 of them. The 3 that are nicest to write. One of them, which is the one when you choose the regular module category, it's always the one that you, well, that is the least easy to write down explicitly, because this is the one that involves the Raka coefficients, and also then okay, you just the formula I wrote down last week, that's the definition. It's difficult to write it down more explicitly. The 3 others, I can write them in terms of spin operators, and so then it's a bit easier to get a sense of how these things work. Okay, so the first one we're going to do is I'm going to choose the module to be so vec. So here, what I mean by vec, I mean the trivial representations of the trivial subgroup, right? So there is a unique. So I write vec because it has a unique simple object, the same way vec has a unique simple object, which is the one-dimensional complex vector space.
You said that if you take a trivial subgroup, then this corresponds in your previous notation to having C to F.
So here the example is rep G, right? We start from rep G. So yeah, so it's kind of backwards. So okay, so how does the Hilbert space look like? So it looks like this. So this choice means that horizontally there is nothing basically. So since there is only the trivial representation there, it's not really a degree of freedom, right? So there is nothing horizontally. So the way it looks like, the only degrees of freedom actually are given by the fact that we are dealing with the two-dimensional representation. So I'm using these dashed lines because there is actually nothing there. Okay, so that's how the Hilbert space looks like in our diagrammatic language. At the end of the day, this is just a tensor product space where I have a copy of C2 at every half integer site. So maybe let me clarify what's going on here. Remember that the action on these guys is going to be given by the restriction. Okay. So if I take the two-dimensional representation, I restrict it to the trivial subgroup, then I'm getting twice the trivial representation. So this index there is just count which copy of the trivial representation we're looking at. It's just some multiplicity. Right? So yeah, so that's the Hilbert space. And now the action. Well, for the action, now we need to work out a bit more explicitly what these F symbols are. But in this very specific case, it's quite simple. So graphically, I'm going to put it there. So as I said before, it's always some contraction of Clebsch-Gann coefficients. It's just that here, since many labels are trivial, in the end it reduces to something quite simple. Okay, so here V1 and V2 are representations, irreducible representation of D6. So given the Hamiltonian we chose, the only thing that could show up is either a 1 or the one-dimensional or the sign representation or the two-dimensional one. And in that case, the F symbol is actually just a single Clebsch-Gann coefficient, which I wrote like this last time. And there is no multiplicity, so I don't have any, there is no choice of basis vector over there.
The bottom line on the left picture should be dashed again.
Oh yeah, yeah. Okay, so now the Clebsch-Gann coefficients, well, I'm not going to write them down, but they are very easy to compute. And then you can just plug that in. So at the end of the day, the Hamiltonian is going to depend, usually it depends on two F symbols. Then in that case, it's going to depend on two Clebsch-Gordan coefficients. And if you just look at the values of these Clebsch-Gordan coefficients, you find that the Hamiltonian, which I'm going to write H-vec for the choice of module, is a familiar, well, hopefully familiar Hamiltonian. So it's just the XXZ Heisenberg model. So at this stage, maybe let me just tell you a bit the intuition, like why, how come the Heisenberg model shows up. So this XXZ model, it has a pretty big symmetry group. You can have you have the symmetry group is basically Z2 acting on U1, and so a subgroup of which is Z2 acting on Z3. So here, what it means is that we are focusing on only a subsymmetry of the total symmetry, which is D6. And what we are secretly using in order to write down this Hamiltonian in this way is the Wigner-Eckart theorem. Wigner-Eckart theorem says that if you have an operator that is symmetric, so the Hamiltonian is symmetric, you can always decompose it in terms of Clebsch-Gordan coefficients. So secretly, this is what we are using here. And actually, this is secretly what we are using all the time. We are using effectively some generalized version of Wigner-Eckart theorem to argue that any Hamiltonian that has a given symmetry, we can always write it down using our recipe. But in that very specific case, it's just the usual Wigner-Eckart theorem. Okay, so this model has, so as I said, it has a D6 symmetry. I mean, not only, but the construction guarantees that it has a D6 symmetry. Then we know, I would say that the rest, the fact that it has a bigger symmetry is more, it's accidental in a way. It's just like, it just happened to be like this because of the specific coefficients we chose. But if I had chosen like different coefficients, then the only thing I could guarantee is that it would have a D6 symmetry. And so this D6 symmetry is generated by, well, there was the usual Z2 symmetry, first of all. And the Z3 part is given by this. Okay?
Clément, you did not discuss the generalization of this line action on your new Hilbert.
Yeah, I haven't talked about the symmetry yet. Here, we just know what the symmetry is. In a second, I'm going to do another example where we don't actually, it's not obvious what the symmetry is, and we will need, so then basically, then I will explain how to derive the symmetry in general. Okay, so let's do this, this other example then.
Sorry, H operator can, okay, you wrote down these two operators, but they all respect U1 in some sense. They all respect the U1 times Z2. Is that's
Separately, yes.
Yeah, so there should be some operator that breaks U1 to D6. Well, breaks the symmetry explicitly to D6, and there.
I could write down an operator. Yeah, I mean, here it just so happened that indeed I chose these operators, and there is kind of this accidental symmetry which is bigger than the one I can guarantee from the construction. I could have, yes, I mean, I don't know off the top of my head, but I could write down one that would for sure break the U1 symmetry, and only the D6 part would. I guess if you take something random, you would break. Okay, so the second choice we're going to do is we're going to choose M to be the representations of the Z2 subgroup. So here the only thing I need is, in order to work out the action, is to give you the restrictions. So the restriction from D6 to Z2 of the sign representation, well, it's just the kind of the sign representation of Z2, right? and the restriction of the two-dimensional one is going to be the sum of the trivial one plus the sign. I'm using kind of the same notation, but so here I'm emphasizing the fact that these are representation in Z2 and not in D6 anymore. Then the Hilbert space. Okay. So the usual, so it's a different type of Hilbert space now. So let me use a different color. Okay, something like this. So the vertical ones are always labeled, so this never changes, huh? It's always the two-dimensional one. But now, for the green lines, well, now we have representations of Z2. Okay. But crucially, there is no multiplicity there. Because if you take the two-dimensional representation, since it restricts to that, when you act on either the trivial or the sign, basically it's gonna, well, it might either give you the same thing or it might flip it, but whatever you do, you cannot have some multiplicity there. So there is no choice of basis vectors in this guy. So now the only degrees of freedom are these choices of rep Z2 degrees of freedom. And so we have a Hilbert space that is isomorphic to the one we had before. But it's kind of interesting to see that it's still a spin 1/2 model in the sense that the local Hilbert space is the same. But it's of a very different nature. It comes from the fact that we have only 2 E-reps in Z2. Well, before it came from the fact that we had a two-dimensional representation. So this illustrates a bit the fact that this Hilbert space is the effective Hilbert space you end up with can come from, you can realize the same Hilbert space in very different ways, essentially. And the model, so the model is actually very simple. So then you compute the F symbols. Again, it's always some Raka coefficient, so I'm just giving you the answer. And you find, so as I said, it's still a spin 1/2 model. And you get a simple looking Hamiltonian. Okay. Something like this. And the symmetry of this Hamiltonian actually is not obvious to derive. Actually, this I'm just gonna tell you, and then I will explain later why. But this model has actually a rep D6 symmetry. And it's actually very difficult to check this rep D6 symmetry without using the kind of the machinery that I'm introducing. So the symmetry can change drastically depending on the choice of module we choose. Something we already, so in this GIZ model I did last week, we have already emphasized that this could happen, and we could go from an invertible to a non-invertible symmetry. And finally, the third example. So I'm choosing rep Z3. So same, I need to give you the restrictions. So the sign representation restricts to the trivial this time. And the two-dimensional one, it restricts to the two non-trivial representations of Z3, which I'm labeling 1 and 1 star. So what is interesting is that another Hilbert space is quite different. And in particular, this is going to be the first example really we consider of a non-tensor product space. I mean, well, the drawing is really the same as always. I'm not sure why I keep doing it, but okay. Okay, so two-dimensional, this doesn't change, and here, so these M labels are irreducible representation of rep Z3. So what is interesting is the fact that, so this guy, M2, can be the trivial representation or one of the two non-trivial representations of rep Z3. Okay. Since the two-dimensional restricts to this, and the fact that the trivial representation does not appear there, it means it's not possible for these two degrees of freedom to be equal. This would require this to contain the trivial representation. So generally speaking, mi has to be different from I plus 1. And so this is not a tensor product space because of this. And also this is a 3-level system because now we have the local Hilbert space is 3-dimensional instead of 2-dimensional. So in contrast to the 2 other models we did. And so this Hamiltonian, what it is, it's actually a constrained clock model. So basically, it's basically a clock model, but that preserves these specific kinematical constraints. So the Hamiltonian, okay, it looks a bit complicated, but it's just to reflect the fact that we have this constraint. So I'm gonna use this this sigma because these are the clock matrices. So this is really just the non-trivial part of the Hamiltonian. The rest I'm writing down right now is just something that is going to project out the configurations that are not allowed. Just to make sure that when you act with this sigma x, you're still you're staying in the same Hilbert space. So plus the Hamiltonian conjugate. Okay, so that's the first part of the Hamiltonian, and the second part is a bit easier. So same. At the end of the day, this is kind of just a sigma z term essentially, but with the additional constraints. Okay. Okay, plus the Hamiltonian conjugate. So this, as I said, this operator is basically just, it acts with this matrix sigma x, which is just the clock matrix. I'm going to put it there. Okay, and the sigma z is just the usual. So this term, essentially what it does is that it acts with plus or minus 1, depending on whether these 2 degrees of freedom are equal or not. So it basically checks it measures the degree of freedom on the site I, but then it measures it, or either it measures it or it doesn't measure it, depending on the value of these guys. Well, it's just something that follows from at the end of the day, from the constraints that come from this tracer object. And this model has a D6 symmetry again, which then is fairly. It's just the kind of permutation of the colors. Basically, we have 3 colors, so we can permute the colors. That's a D6 symmetry. So this is, you can eyeball the symmetry in that case as well. You don't really need the machinery, but for this one, you would actually need it. So after the break, I will explain how we actually derive the symmetry of these dual models. Okay, let's stop here. So now I'm going to explain how we going to essentially compute what we call the dual symmetry is. So after, even though I haven't yet shown you in which way these models are dual, I'm going to, given a choice of module category, we're going to see what is the symmetry in general. So the intuition, let me just rewrite my Hilbert space. Generally speaking, it looks like something like this, and then I have these degrees of freedom in my module category. So what is kind of important to think of is that we should think of the module degrees of freedom they're always in the module category. Sometimes it's slightly misleading, because in the choice we did earlier where we chose vec for the module, and here it was all the 2-dimensional representations, the degrees of freedom came from the fact that we have a 2-dimensional representations. But this was still maps in the module category, right? So the degrees of freedom are always in the module category. The vertical line labeled by x, it's just like putting some additional constraint on the kind of Hilbert space we consider. So a symmetry. So what is the symmetry? So given that choice, so here I have a choice M. This is M there, and I have my choice C. Right? So what is the symmetry? So first of all, so I'm going to try to kind of motivate what it is. Well, first of all, it should be some operation or map that takes module degrees of freedom to module degrees of freedom, right? Because these are really your these are really the degrees of freedom. So first of all, we want something that take so objects and morphisms in the module category to objects and morphisms in the module category. So this is what we call a functor in the category-theoretic language. Then this is, you can think of it as an action essentially, like it's a way of acting on your degrees of freedom. And this action, so we must preserve the Hilbert space, right? Or Hilbert space in general, it comes with some constraint. So this action, it must preserve it. Which means in particular that this operation must commute with the action of x. If not, you would kind of disrupt the structure of your Hilbert space. So this means that sort of f needs to commute. So when I say commute, I mean it can up to some isomorphism in the same spirit as everything we've done so far, the associativity and so on. It's always up to some isomorphism. It needs to commute with action of C. Also, maybe motivated at this point. So remember the symmetry operators, how they acted initially. Remember that we had to use a move, an F move, to pull the line past an object, right? And we use an isomorphism for that. This is the same thing I'm talking about here. Something that whether you act before an object or after, it shouldn't matter. Otherwise, if it did, then it means you would break your Hilbert space. So concretely, what it means is that we must have some isomorphisms of this form. So this is the way I'm writing. I think of it as a function on objects. This is literally means whether you first act on this degree of freedom and then react with x, it should be the same as up to an isomorphism with first acting with x and then acting with what is going to be ultimately our symmetry. So this gives you, so if you have this, then you have a well-defined kind of action on your Hilbert space. But there is no guarantee that it's going to commute with the Hamiltonian, right? So the commutation with the Hamiltonian requires that these isomorphisms, so it's the same story, yeah? Requires this omega I wrote to satisfy some coherence relation, which is always some type, it's always what we call a pentagon axiom. So by the way, I don't know if I clarified, but we call this pentagon axiom because it's the way I'm going to draw it again now. You have like 5 arrows, so it always looks like a pentagon. So this commutation relation that I'm going to write, it will ensure that this well-defined action on the Hilbert space commutes with the Hamiltonian. So to do this, we're going to do it graphically as much as possible. And so I need to introduce the usual notations I introduce in order to do this graphically. So let me introduce some notations. So first I'm going to use a shorthand for, so I have two things here. I have the F really, and I have this omega. So generally speaking, I'm going to just label this with one kind of object, right? Y. So by Y, I mean some F and some omega, okay? And I want to write this action of F graphically using, relying as much as possible on what we've already done. So I'm going to consider, so I'm going to write this, I'm going to try to be consistent. I'm going to write these new types of lines in red. Okay. So this one is labeled by Y. And here we have, so a degree of freedom in M, an object in M. simple, and here another one. So here, what this represents, it's a vector, which is labeled by, so this labels y, m1 and m2 labels which vector space I'm talking about, and then j is a basis vectors in this home space. So very concretely, this is this guy. I'm acting with my f on m1. This, it's still an object in the category, but it may not be simple anymore. It's possible that it's not simple. And m2 would be an object that appears in this decomposition into simple ones. So I'm going to introduce this notation for this type of M space, like in the same spirit as one notation I introduced for the home spaces in C.
This y is an object of C, or is it still another category?
For now, it's going to be yet another category. Yeah. For now, it's just some object. We don't know yet what it has to be.
So now you're making your M. Before it was a C module. Now it becomes also some C tilde module of some other category.
Yeah, exactly. From the other side, from the left. Okay, so what I want to do now is I want to spell out what these guys are. So exactly the same way we spelled out the F symbols, the F action symbols. This one, I want to write them down in terms of matrices. It's always the same story. So this is always this is going to be some new type of F symbols if you want. So the first thing I do is that let me just rewrite the isomorphism I'm interested in with the notation I just introduced. Okay, so this is this guy I want, and this boils down to some, I can block decompose it, and it boils down to blocks like this in particular. So it's an equation that is very similar to the one we had in the case of the F symbols. I'll do the corresponding drawing in a second. Okay, and so then I can further decompose it. I can pick an M3 and an M4. I get a matrix, and now I'm going to depict the action of this matrix. So using my three colors. Wrong start. Okay, so these are the module degrees of freedom in green. I have the action of my object X here. Okay, and my new line acts here. Okay. So this is the left hand. This is the first I'm acting with Y. And then I'm acting with X. Okay, this is the left-hand side. And the basis vectors are labeled by J and K as usual. Okay. So I have my new set of complex numbers. So the notation, the distribution of the indices, it's meant to follow as closely as possible what we've been using so far. Okay. And now I have okay. Okay, so this is really, we can move a red line, which is going to be ultimately, a symmetry operator, past the action of X. So this is a complex number. Okay. So now, how does it look like, the action? Well, it's exactly, it's very similar to the first thing we did. So we have our Hilbert space, which looks like, okay, we have our X degrees of freedom in C, like this. And now we act, the symmetry line is going to act in the same way as we did initially, from the bottom, like this. The fact that we have, so we, the F plus this, or rather just the F, the fact that we are in action, it means I can sort of, you know, absorb this red line in the horizontal one the same way we did it initially. Let me just draw it and switch.
It was an axiom for that in the spherical category.
Yeah, well, it's there is an analog axiom. There is an analogous axiom there. Yeah, so it is actually a bit more subtle, but yes, it's we can do the same thing. Okay, so the way it looks like is something like this. So we have our no. Okay, and I absorb it like this. Sorry, I have one too many. Okay, so I do something like this. I do it everywhere. Then I'm going to use this operation in order to move the red line past the white line. So I'm going to use repeatedly this move, like this omega move, if you want, to get something that looks like this. Okay, so you do this everywhere, so you have it here as well. Well, yeah. Okay, it should be green. Okay, something like this. Okay, and then you can just pop the bubbles the same way we usually do, in order to go back to something of the initial, of the same form as before. Okay. So that's the way it acts. And now the fact that it commutes with the Hamiltonian, so we can also do it graphically. Well, rather, I'm going to give you the pentagon axiom, and then from this we will infer the fact that it will commute with the Hamiltonian. So the pentagon axiom. So loosely, it's something that. So it's always in the same spirit. We consider one more object. So I'm adding a white line, and then I'm saying that to go from so this configuration of lines to the one to this line to this one over here. Oh, wrong color. To this one over here, there are two different paths you can follow. So the first one is this one. Okay, so then I'm first doing. I'm first using the module associator. So here I'm using this F. I'm changing the order. I'm fusing these two lines instead of acting with these ones. And then to go to here, I'm using my omega. Okay. And now the other two options. Well, the other path rather. Okay, so we get something like this, and here something like this, and like this. Okay. And so this move here, it's an omega as well. So we get a mixed coherence correlation that involves both the omega and the F, which is not surprising, because these things are what enters the definition of the Hamiltonian. This thing is what enters the definition of the action of the symmetry, and this coherence correlation is going to ensure that it commutes. And so the argument is exactly the same as the one I used previously. So if I consider this configuration, okay, so I have keeps going like this, and here I have my action. Okay, so locally, let's say I have this is the action of my Hamiltonian. The symmetry looks like this. Now, in order to resolve this diagram, I can first take care of the Hamiltonian part. It's going to involve these guys. Or I can first take part of the action of the symmetry by moving this past like this. And this diagram ensures that the order in which I do these operations don't matter. And this is what guarantees that it commutes. The action of the symmetry commutes with the Hamiltonian. So this is what gives you the commutation. So you may have noticed that in general, these symmetry operators, as before, they are not local, right? They are non-local. They are going to be non-local operator in general. And so actually checking the commutation relations can be a bit difficult. So in the case of the example I had before, where I claimed there was a rep D6 symmetry, it was a non-local operator. These are typically difficult to write them down. Usually we write them down as matrix operator. It's a nice way of parameterizing them. But even then, it's difficult to check the commutation relation explicitly. Often we just rely on the fact that it has to work by construction like this. Okay, so what is it I'm saying by putting everything together? So if I take, so my object F, this guy, with the collection of isomorphisms plus my pentagon axiom. So I needed all this in order to claim that this was a symmetry. This forms actually a well-defined algebraic structure that we call, so they are all organized into another category, which is called a category of C-module functors. So this, the object we just described, putting all this definition is the definition of what we call a module functor. So it's essentially a map from M to M that essentially commutes with the action of C. That's all what it's saying. And this, it has a special notation. So this category, it's written like this: func for functor from M to M, M to M, and the C is to remember that this is of C module functors. So there is a special notation for this guy. And it has a special name as well. It's called the Morita dual of C with respect to M, which is also saying that this guy is Morita equivalent to C. So it's a type of equivalence. And the dualities we're talking about is basically just a realization of this equivalence. The reason I'm phrasing it like this is that, okay, first of all, a lot of these things have been computed in the past. So this is why also I'm specifically using it in that language, because then we recover an object that has been extensively studied, and there are many examples of C and M where we know exactly what this is already. And these computations can be quite difficult, so it's very helpful to be able to rely on some computations that people have done in the past. And this notion of Morita equivalence is also really crucial, because this is what will guarantee ultimately that we have the same sectors a model and its dual. The sectors will be labeled by exactly the same thing, and this is really what at the end of the day will guarantee that we have a duality.
Is that why you've written it as like C?
Yeah, it's basically dual. You should read this as the dual of C with respect to M. And so any M I took for any M, they're all dual to each other.
Is it still a fusion category?
Yeah, I was gonna say something about just now. So this is precisely all the assumptions I've been making without emphasizing them too much. The fact that M is semi-simple and everything indecomposable. This is precisely to make sure that C with respect to M is indeed a fusion category. And we can work out, so the data we miss right now is the fusion, right? What is actually the fusion structure? But this actually, so the fusion is provided by the composition of module functors. So this has maps, from M to M. You can just compose them, and this composition will just provide you the fusion structure. So the monoidal, the usual, what I write usually with the tensor product. In that case, the tensor product for this comes from the fact that you can compose these maps. Now this is difficult to, so sometimes working out the category, just knowing what are the objects this is not so bad. Working out this is much more delicate. So the fact that many examples have been computed before is a big help. So maybe let me do just one very simple example of this computation, just to get a sense of how it works. So this example is, so I'm going to compute the dual of vec G with respect to vec, right? So I'm just applying the definition. This is something like this. So this, I mean, well, in principle, you already know the answer. This would be, I start from a G symmetry. So first of all, you can fairly easily convince yourself that if you take the regular module category, the dual is itself. So if I take the dual with respect to itself, it's just itself again. So by changing the module from vec G to vec, it amounts to gauging, and we already know what's going to be the resulting symmetry after gauging. This should be equivalent to rep G. This is the interpretation of this computation. And so how does it work? Well, this is a simple case. So I have, so let me take an object f omega in there. So what it is, it's a map. So it takes the category of vector spaces to itself. And so in the same way as a map from, complex number to complex number, it's just a complex number, right? Here, the map from the category of vector space to vector spaces is just going to be given by a vector space as well, in the sense that this map is fully specified by the way it acts on the one-dimensional vector space, and this is some vector space. I don't know what it is. It's some vector space. I call this vector space V, and then my map omega. So by definition, what are they? They are map. So it's enough to look at only the simple objects for these things. It's a bit like the basis vectors. I'm only doing these computations. Basis vectors. So this I know what it is. It's V. This, well, it's C as well, because the way vec G acts on vec is essentially by forgetting the group. It's like you just forget that you have some group elements. So here then it's just the tensor product of C with C. So it's C again. And then the action of this on C is V. And then same story, the way this guy acts, well, you forget the G, and then it's just you tensor with the one-dimensional vector space, so nothing happens. So this thing is just a map from V to V. And I'm just going to write it down like this. This is just a map from V to V. And then the Pentagon axiom. The Pentagon axiom is just, you can just go back to the drawing and see that it just implies that, so there is no, the Pentagon axiom here, there is no F, this F, the module associator, it's all the identity, right? Because there is no, co-cycle here, there is none of this, so it's all the identity. So only the omegas, you can just forget about the F's, you just look at the omegas. And then this diagram is just saying that it composes nicely like this. So this is just the statement that this F with this omega, it defines a representation of G. Just to get a sense of these computations, but already here, this example, it tells us, as I said, if you gauge the whole symmetry, then the dual symmetry is going to be given by the dual of vec G with respect to vec, which we can verify is rep G, as we already anticipated.
So the Pentagon axiom is literally saying that you get a representation of G out of the omega. I'm not sure.
Yeah, so here, I mean, if you just look at the omegas, what you see is that, I don't know, if you label the two white lines by G and H, you're going to get omega G first, then omega H on one side, and then on the other side, you see you fuse first G and H, so it's going to be omega GH. So the fact that two paths have to agree is just saying that omega h term composed with omega h has to be omega gh. Okay, and so the example we had at some point, we had earlier, for instance, there was this other example where we started from rep d6, and well, we took the dual with respect to rep z2, right? This was the we made the choice of module category, which was rep z2, and I claimed that the symmetry was rep d6, and this is because this actually is equivalent to rep d6. It's a more delicate computation to do, and then I don't really have a nice way of writing down the symmetry operators. This is a case where we do actually have to employ this whole machinery because it's difficult to write them down. It's non-local, so the only way we have to write it down somewhat efficiently is as a matrix product operator, which directly comes from this definition. But the fact that we knew that it was rep d6, it was because we knew that this was the case. And all the other examples is the same. We can. So the other example, then, for instance, rep z3, then we know that this is actually vec d6, which is why we had the d6 symmetry as well.
Is there some reason that you're doing this duality is only these two types of categories come up, either rep or vec?
Sort of, yes. So as I said, d6. So this is kind of specific to this example because it's quite small and it can get pretty. So you can have, for instance, if I take, so you have, if you take like slightly bigger dihedral groups, you can have some anomalies that show up. Even though you start without anomalies, some dual symmetries have some anomalies. So it can get more crazier than this. But in that case here, the intuition is the fact that, okay, I have this. So when I gauge Z3, which is a normal subgroup, this is usually a case that is fairly easy to treat. What happens is that then you just dualize. It's like you forget kind of about the Z2. It's as if you had a Z3 symmetric model and you just gauge that Z3 symmetry. And so then you get the dual of Z3 with respect to vec, which is, well, it's abelian, so then it's Z3 again. It would be technically the dual, the Pontarlian dual of Z3, but since it's abelian, it's Z3 again. So this is what happens here. Technically here, the D6 there, you might want to think of it as this actually. We did dualize the Z3. Every time you do something with a non-normal subgroup, which is the case of Z2, this is when things become a bit more exotic. So for instance, yeah. So yeah. Okay. So now we can talk about the duality operators, which actually are defined exactly in the same way. So, I mean, at this point it becomes almost intuitive, right? So if I have, so given, let's say, two models. So first of all, let me clarify exactly what I mean by duality operators now that we have Hilbert spaces that can be different, right? So given two models that only differ, so let me spell this out, that only differ in a choice of module category. Of C module category. So what it means is that the abstract local operators are the same. I'm just changing the Hilbert space, right? So we want, I'm looking for some operator, D, that goes from the Hilbert space with respect to M to the Hilbert space with respect to N, okay? In such a way that, so this, remember, these are typically non-invertible, so we're not going to act by conjugation on the Hamiltonians. The way you want to, the way to think about the action is via some commutation relation of this form, because we can't put the two D's on the same side since it's non-invertible. And so this will be the statement that, okay, I'm going to use sometimes the word like I'm transmuting the Hamiltonian into the order. I want to avoid, I'm saying duality operator, but at this stage it's just something that transforms the Hamiltonian into the order. To really have a duality, as we said, we have to work out the sectors. And so this almost intuitively, since they only differ by a choice of module category, where this is going to be something that is labeled by, so a functor from M to N. Instead of taking maps from M to themselves and then satisfying all the axioms, we're going to do exactly the same thing, but now from one module to the other. So actually, we don't really. I'm not going to do it explicitly, but what it means is that this guy, so it's labeled by the same type of data. The only difference is that now F is a map from N to N, and omega, well, it's kind of, it's even more mixed than before, because now I have two types of actions, one with respect to one module and one with respect to the other. So I'm using this action prime for whatever is the action in N. This omega must satisfy exactly the same type of conditions. The only difference now is that above and below the red line, and now these are different types of degrees of freedom. So I'm not going to write the Pentagon equation, but let me just give you at least to fix some colors, if I have enough. Yeah, so it's becoming a bit but so okay, I'm just gonna do this drawing to clarify. So I have so I'm using red for the duality operator as well. And I'm gonna have to use the blue again because I don't have enough colors otherwise. So we get something that looks like this, right? So I have my duality operator, which change from one type of module to another. And X is as before. And so on the other side, you have something that looks like this. Blue, white, and red. Okay, so this is the new type of omegas, like this. Okay. These have to satisfy, so as I said, the Pentagon equation, which you just do the same as before. You just add this new color. And this Pentagon equation is going to ensure the fact that it does transform one Hamiltonian into the other. So basically, the Pentagon equation now is going to have three omegas as well. One module associator of M, the module associator of N. And in the same way, for the symmetry, it ensures that the action of the symmetry commutes with the action of Hamiltonian. Now it's a different type of commutation relation, but it's going to transform one module associator into the other. So the action, the way it works. So let me just do this bit. So we start from a Hilbert space like this. Okay. I have my duality operator like that. Then I absorb it as I do usually like this. But now as I do this, it's going to act on these green degrees of freedom and give me the other type of module. So I have something like this. So something like this. So here, this is the result of the action. So I have this new color, and now I have the previous one. And as I pull through my red lines past the white lines, then it's going to be all blue everywhere. And so eventually, you get to something that looks like this, where it's all blue like this. Okay.
And you know in advance that this category of functors from M to N is not something empty that you have these functors?
Yes. So it can be, so in some cases, there is a unique object in these categories. So for instance, when we gauge everything, there is a unique way essentially of doing it. Because if you take so again, the same way we know a lot of Morita duals, we know a lot of examples of these guys. So if you take the module functors from vec to vec, which amounts to gauging the whole symmetry, this category is just vec, which means there is a unique object. So there is a unique way of gauging. The freedom you get when you have several duality operators is not super crucial. It just means that it can kind of permute the states a little bit, but it's not nothing major. It's like a kind of a basis transformation the same way we gauge. But so it's never going to be no, it's never going to be empty. There will always be a choice.
And also, so an action of D is just this procedure with adding the red line and merging it.
Yeah. So I'm just going to try. So as in the first course, I explained that in practice, I wrote down the duality operator as a matrix product operator. Let me just like sketch very briefly how it looks like. So as you see, we get this kind of local contribution. Even though it's a non-local operator, we can decompose it into some local contributions. So I can write down my duality operator in the spirit of what we did for Clément as something of this form, right? So I have this 4-valent tensor that I'm contracting, and at the end of the day, it gives me an operator from top to bottom. So I think of this as acting. This is my initial Hilbert space. That's the new one at the top. And so these guys, then we know exactly what they look like. It's just they are a bit complicated in general, because the indices are valued in some Hilbert spaces that are kind of constrained in a very specific way, which just follows from the way the Hilbert space is defined. So if I specify these indices like that, using the notation we've been using, okay. Well, this is just, so this is the component of my tensor Y. This thing is just given by the symbols associated with the module functor. So that's the way to, I don't know, maybe for some of you it's easier to think of the duality operator like this. Just to say that at the end of the day, we can write it down as a matrix. And so if I'm given a state, I can just plug in that thing and then we just work it out.
So do you have the same homology class for MNF?
The same homology class?
Homology class.
Of the module category? I'm not sure what the homology class of the module category is. What do you mean?
Well, for example, you start with G, the homology class of G.
So here MNN, I mean, this can be, there is not necessarily a group here. I mean, the input C could be any fusion category, right? But okay, otherwise, yeah. So for instance, no, you could take two different module categories with respect to two different cocycles. So in some cases, so then you're gonna end up with some kind of projective representations, typically given by the ratio of these cocycles or something like this. Yeah.
Can you get like abelian and non-abelian map with F?
So yes, so for instance, you can have, so as I said, you can have, for instance, a symmetry on one side which is non-abelian, on the other side it's going to be abelian, but with an anomaly, so you will have a 3 cocycle there. So then the corresponding module category, I don't know, I mean, it depends on the group, but yeah, it can be, it can get pretty wild, these mappings, yeah. Yeah.
Does the map D, does it have any like, does it have certain properties, like does it have to be isomorphic?
So this is D, right? Basically, this is D. D is that. Well, its property at this stage is that it maps. So if I take my Hamiltonian on one side, I pull it through that thing, I get the Hamiltonian on the other side, right? From this, you can also infer the fact that there must be some sectors where this is invertible. So it gives us like one piece of the duality. One way to see that is that I can do the opposite operation. I can go from n to m as well. So it's not, this is not invertible, but I have a notion of opposite. So I can go from n to m. We established before we could compose these functors. So the result is going to be a map from m to m. The result is going to be a symmetry, actually. But the fact that D is not invertible means the resulting symmetry is not going to be the identity in general. And actually, what you will get, basically the symmetry, or it's going to be a sum of symmetry operators. This is going to be the projector on the corresponding sector where this is invertible. So in the case of Ising, if you take Kramers-Vanier and you do the dual of, the opposite of Kramers-Vanier, as a symmetry, you get 1, the identity, plus the non-trivial one, and that's the projector onto the even sector. So that's in general the way it works.
Yeah. Given two module categories, can I define a new module category where the simple objects are the collection of the simple objects from the previous two categories?
You mean, can you tensor module categories? Yes, you can.
Tensor product. I just want the simple objects to be the simple objects of the first category and
you can. There is a notion of tensor product of module categories or Deligne product of categories. Actually, it's very similar to computing the dual. The map from n to n. But yes, you can take two module categories and then consider like simultaneous action on these two module categories, and this is going to decompose into indecomposable module categories. So you can do that.
Okay, so suppose say I call this new category m tensor n. So then if you have this functors from m to n and also the one from n to m, then also including the functors from n to m and n to m, can you promote all of these functors to be the symmetry of this bigger module category?
Okay, I'm not exactly sure this is what you're asking, but let me say this, which may be the answer. What we do ultimately in order to prove the actual duality on all the sectors and all, is that you can build some kind of super category. Well, I shouldn't say super. Some big category where you have the original one, you have all the duals with respect to the module categories, and also all the maps from module categories to others. So you can consider some kind of big object like this. And this is going to be, it's not going to be a fusion category per se, but it's going to be a well-defined object as well.
That sounds similar. My question is motivated by the symmetry enhancement at critical points. So for Ising, for example, so you can force the duality to be a symmetry. And then you have a bigger...
Oh, I see. So indeed, you can... Okay, I see what you mean. So yeah, that's for instance what happens for Ising. So you have a duality which happens to be a self-duality. And in that case, so there is a process to do this. But indeed, the idea is that you can incorporate this self-duality to your original symmetry, provided that some obstructions vanish and everything, and then build a bigger category from this. So for example, the Ising fusion category, which contains the three topological lines of the Ising CFT, it is an extension of Z2. It's something that you start from Z2, you add the self-duality Kramers-Vanier, and you get something bigger.
So I really was curious about whether you can do this given any C, M, and N, or whether there's something special about Ising or maybe...
No, you can. So you have some obstructions. So the question is whether the starting point is usually an invertible bimodule. So when you take M, so you see graphically what we have is that the green line is acted upon from the left by the red and from the right by the white. So this gives it a bimodule structure, and the fact that the red is the dual of the white, this tells us that it's an invertible bimodule category. So it's an alternative way of defining Morita equivalence, which is closer to the usual Morita equivalence of. So in general, you can ask, if I have such an invertible bimodule, can I include it in my category, right? And so sometimes you have some obstructions. You cannot always do that. You have some cohomology classifications of obstructions, and you have to make sure that they vanish. You have several layers of obstructions, and if everything vanishes, then you can actually do this process of promoting the self-duality to a symmetry.
Does it say something about the physics of when critical point and self-dual point coincide, or is it just something technical?
I don't think so. Because it's a purely symmetric statement. Whether the self-dual point is also a critical point, it's more specific to your model. So I can't imagine that you would be able to say something definitive. Yeah. I think we should. I'm gonna stop here. So if you have further questions, just yeah.
But in fact, it is a little bit strange that, so in the usual treatment, okay, so there is symmetry, and then you write a Hamiltonian, you may want to write a Hamiltonian which respects symmetry, you may want to write a Hamiltonian which breaks symmetry.
Mm-hmm.
Here somehow, in the zeroth approximation for you, the Hamiltonian and the symmetry, they kind of appear as a part of the same framework. And so the Hamiltonians, so the nature of the Hamiltonians which arise, they naturally respect all the symmetries that you're considering.
Yes. Although
if suddenly you acquire some extra symmetry, like this duality, which you want to interpret as a symmetry, you have to do some extra work.
Oh yeah.
Which in the usual approach that we are used to with groups and everything, there's no such problem.
Actually, it's very difficult in practice to promote a self-duality to a symmetry.
Why do you have to promote it? So because you said symmetry is always some. You first convinced us that symmetry is always some functor, and you told us that functors have been classified. And then suddenly you say, oh no, with duality we have to promote it, but then if everything has already been classified, then means that mathematicians have.
So then what you do when you promote the self-duality to a symmetry is that you change the C, you change the input. Already with Kramers-Vanier, this is very subtle. Kramers-Vanier, if you just look at the Hamiltonian, we see the mapping, and we say, okay, if you're at the critical point, it's a symmetry in the sense that you swap the two terms and it looks invariant. Now the question is, can you make this an internal symmetry? Can you really make it like an actual, like an internal symmetry? That's basically what I mean when I say promoting the self-duality to a symmetry. And actually you cannot. What happens is that, so if I start from the Ising fusion category, which we know is the symmetry in the continuum limit, and I try to write down the lattice model from this, I'm getting two copies of the transverse field Ising model at the critical point. I'm not getting only one, I'm getting two, which kind of get sort of swapped as you do the Kramers-Vanier. So it's still good because it kind of pinpoints the critical Ising model, but we get two copies of it. Then you could ask, and this was recent work by Schuring-Schau and Seiberg, they said, okay, let's see if we can, they tweaked a bit the duality, they made sure that it acted on the same Hilbert space, so there was no going from integer size to half integer size already, this is a bit problematic from a symmetry point of view, so they made sure it was on site. And then what you realize is that if you apply twice this Kramers-Vanier duality, you don't quite get the fusion rules that you expect from the Ising CFT. You get an additional contribution from a translation operator. So these are the two different, these are just two sides of the same coins. But in any case, you have some anomaly essentially. You cannot write down, at least that's the current understanding, you cannot write down a lattice model on a tensor product space that has strictly the Ising, the symmetry that we expect in the continuum limit at the critical point. So
you'll never be able to satisfy which equation fails.
You won't be able to write down essentially this Hamiltonian, the critical one, in such a way that you get like three symmetry operators that act like an internal symmetry labeled by three operators: the identity, the fermion, and the sigma. and what the sigma would amount to swapping these two. If you do, so this you can do, but then the fusion rule of the sigma is not the right one. You get this additional translation operator that shows up.
In addition to translation operator, nevertheless, the fact that it's present, it's not a problem for the symmetry operation commuting with the whole Hamiltonian.
That's indeed, that's not a problem. In that case, the problem is that this is not the it's not even a fusion category in that case, because you have a translation operator. So this is not what we expect from the continuum, from the continuum story, right? Well, in the continuum, you have genuinely the Ising symmetry. By Ising, I mean including Kramer's-Weini. Yeah. It's not saying that you cannot write. There are certain models where the self-duality can be. It is possible to have the expected fusion category that includes the self-duality, but for Ising, the understanding is that we can do that.
It's just I don't understand the rules of the game. And I see whatever commutes with Hamiltonian and next on the Hilbert space is a symmetry. Now you're saying, oh no, there is a translation operator.
Well, for us, the commutation with the Hamiltonian was, even though I haven't emphasized that point too much, it's actually more of a consequence of it being a topological operator. And the rules of the game is that I said I'm considering only operators that are encoded in some fusion category. What I'm saying is that to do this, I can write down an operator that commutes with the Hamiltonian and so on, but then it goes beyond the sort of established framework, which is not saying that we're not saying that all the symmetry should be that framework. It's just that we know that everything works nicely when it's that framework. So it seems that in order to accommodate that, we have to go beyond the established framework of fusion categories, and it's a bit in a way that is a bit well, unusual, because the translation operator it's not just weakening some assumptions that I've been making. It's a different type of modifications, which for now we don't really understand exactly what how it works. Yeah.
So these Morita duals, by construction, knows about the symmetry operators that act from the bottom. Do they know anything about what are referred to as charges in our previous lectures that look like Hamiltonian but maybe more non-local?
Well, knows about it. So, for instance, what happens? I mean, I don't know exactly if that's your question, but like, if I take, for instance, some order parameter so it would be a charge operator for a given symmetry, and then I change the module category, so effectively then I go to a dual model. The same thing is going to act differently now because I'm changing the Hilbert space, and it might become a disorder operator, for instance. In the case of Ising, that's what happens, right? You have this mapping from order to disorder, right? So you ask if the symmetry knew about the... Not really, because it's purely at the level, it's above the module category. So these operators, the data that enters this operator, if you want, it only depends on C, right?
Okay, so the order parameters are not related to this module.
Well, it's order and disorder. It's like whatever you... Yeah.
So they are not related to... They do not fall into the framework of this Morita dual.
Well, they get mapped onto each other upon duality. But no, they are. It's something about C, right? It's something about C itself, I would say. Yeah.
Can you say briefly what remains to be done? Because it seems like.
No, we're done. I mean,
this language.
We're done for today. We're done for today.
That this language, which is a gift of Ettinghoff and whatever in the book. You read that book, now you can write whatever Hamiltonian if you're in this language, and you will look up in some tables that mathematicians worked out, whatever, these Morita duals, and now you know everything you want to know. So
the next bit is that we
construct all sorts of beautiful dualities.
Yeah, I mean, so it gives you a systematic way of generating dualities, right?
Infinitely many dualities.
Not infinitely, because you have actually finitely many decomposable module categories. So only we can it's classified, and we know all the possible dualities within these assumptions you can write down. Then you could weaken some assumptions, but
isn't the number of fusion categories infinite?
Oh yeah, yeah. Oh sure, yeah. I meant given a fusion category, then okay. Yeah, so the next step will be to see. I mean, it's very similar to what we did already. It's just to explain how to build these boundary conditions in general, in order to have all the sectors of a given model. Once we have this, then we can actually relate the spectra of the models. And this is the thing we need in practice. This is the information we need in practice. If you want, so I'm going to briefly mention some applications on Friday, but like there are cases where it's conceptually advantageous to go to a dual model, which is typically what you would hope for from a duality. And I'm not.
There's such examples. In some cases, the Hilbert space was.
Sometimes sometimes it's the Hilbert space has a smaller dimension, so that's already a good thing. But also, when we do this duality, we also have a control on the mapping of the phases. So if I start from my Hamiltonian right now, they have a symmetry, but then they can describe different symmetry breaking phases, or maybe some SPTs as well. And I'm gonna show that we know if we're in a given phase and we do a certain duality, we know in which phase we're gonna end up in. And some phases are much nicer to simulate than others. And so this is the type of things, I mean, I at least personally am interested in that case, is that we will use the explicit operators that we have to study a dual model in a given phase, and then we will just apply the duality operators to get what is the corresponding state in the original model. So then in that case, it's a computational advantage. Also, this type of reasoning gives you a lot of conceptual, so I already mentioned the thing we just know how the phases are mapped onto each other via using this reasoning. But also, there are many things you can infer. For instance, you can ask, I don't know, if you have a symmetry, I have a model with a given symmetry, is there any chance of finding a self-duality? Is it possible that if I do a certain, like regardless of the model, since we know what is the dual symmetry is going to be, if we know that duality changes the symmetry, then there is no way I can have a self-duality with respect to that symmetry, because, okay. And so then you can use this type of reasoning, in particular in higher dimensions, to try to say, okay, can we classify what are the possible self-dualities that can be found? And in higher dimensions, you realize, in particular in 2+1D, that there are very, very few of them you can find, as we might expect from the fact that Kramers-Vanier does not give us a self-duality anymore. So you can actually kind of almost classify these things. You can say, if you want a self-duality, it's going to have to be of that type, and it's going to be a bit boring. So this, I mean, yeah, that's just some examples.
We're looking forward to the last.
Okay. Thank you.